Guys, this is section 10.2, comparing two means, and in this section, we're gonna talk about comparing two means for confidence intervals and for hypothesis tests. Okay, now before we jump into this section, this is gonna be kind of a fairly long video, guys. All right, let's kind of review something that we talked about when we covered random variables. So if you remember way back, we covered random variables. I think that was in chapter 5 or chapter 6. We might have had, I think we had a problem that talked about large cups and large lids. Okay, and we told you that the cups followed, the size of the diameter of the cups followed a normal distribution, and that lids followed a normal distribution. Okay, and our question was something like, what's the probability that a lid doesn't fit a cup? So what we did is we had to combine these random variables. Okay, so when we did that, since both of these were normal, when we took the difference, lids minus cup, the sides of a lid minus a cup, that would also be normal. Okay, and then, you know, the lid should be slightly bigger than the cup to fit on it. Maybe it was like 0.04, for instance. Centimeters, millimeters, whatever. Okay, and if it didn't meet a certain threshold, if it wasn't within like 0.01, all right, that's only if it fell outside of that, either way, all right, then it wouldn't work. All right, so when we found this mean, all right, when we combined them, we had to take the mu of the lid minus the mu of the cup. All right, and the spread of this, okay, the spread of the combined, okay, or you could say difference instead of combined, maybe I should call that difference. All right, we're never allowed to add the standard deviations. Okay, all we are allowed to do is we always have to add, but we add variances. So the variance of the lids plus the variance of the cups, and to get the standard deviation of the difference, we would just take the square root of that. So remember, if there's some sort of difference going on, even if it's a difference, you still add. Okay, you add variances. So just keep that in mind as we start to go over this note card. All right, so let's go through it. It says, we compare the populations or treatments by doing inference about the true difference, mu1 minus mu2, between the parameters with confidence intervals or hypothesis test. We use the mean response in the two treatment groups, X bar 1 and X bar 2, to make the comparison. Okay, so just like populations, we're going to have two distinct groups, each one with their own sample means, their own sample sizes, and each one has their own true parameter. So when you start to look at the sampling distribution of a difference between two means, okay, assuming it meets certain conditions, hopefully it's some sort of normal curve or something that looks like a normal curve, all right, we would expect the true center of that to be the true difference between the means. If you looked at all possible sample differences, okay, and each one of these points on that curve, each point represents a specific X bar 1 minus X bar 2. Okay, just like when we had a single sample, we expected the true mean to be down the center, okay, and each one of these dots to represent a specific sample, and we would plot all possible samples. Okay, now it says conditions for the sampling distribution of this. So we're going to be focusing in on this type of sampling distribution. All right, it says when the population distributions are normal. So if I know that the populations have a normal distribution, then I know that the true difference would also have a normal distribution, just like the cups and the lids example. Okay, and then therefore, the sampling distribution would flow from that, and that would also be approximately normal. Okay, so if the populations are both normal, we're set. Okay, or if both sample sizes of both groups are bigger than 30, all right, if the first one's bigger than 30, then the first sampling distribution of mu1 would be approximately normal, and if the second one is bigger than 30, then sampling distribution for x bar 2 would be approximately normal, and then when you combine those, we could say that that's approximately normal. Okay. And the mean of the sampling distribution, again, this curve right here, of x bar 1 minus x bar 2 is mu1 minus mu2. That value would fall right down the center. Okay. And then as long as the independence condition is met, this is the 10% condition, as long as the population is at least 10 times bigger than each of the respective sample sizes, then we can use this formula. But back in, I believe it was chapter 8, right, we couldn't actually use this because we didn't know sigma. We didn't know the true population standard deviation. Okay, these are unknown. The unknown parts are sigma 1 and sigma 2. So because I probably don't know that, in place of that, I have to use the sample standard deviation rather than the population, because I don't know it. All right. So just like before, okay, if I have to use an S instead of a sigma, that keys me in that I have to use the T distribution instead of the Z distribution. Okay. So we have to replace these things with these things. Okay, so this would be considered a standard error. So let's look at an example. So it says a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed by the machine follows a normal distribution with mean 27 ounces and a standard deviation of 0.8 ounces. All right. So this is when the large setting is chosen. So I know that mu of L, the mean of the large, is 27, and the standard deviation of the large is 0.8. Those are both in terms of ounces. All right. It says when the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution with mean 17 and standard deviation 0.5. Okay. So that follows a normal distribution for the medium. It also follows a normal distribution. Mean of the medium, okay, 17 ounces with a standard deviation of 0.5 ounces. That's this information. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled with the large setting. And, okay, so that's important. So my sample size is 20 large cups. All right, so N sub L, sample size for the large is 20. And the sample size for the medium is 25. Let x bar L minus x bar M be the difference in the sample mean amount of liquid under the two settings. So part A says, what is the shape of the sampling distribution of XL and x bar L minus x bar M and Y? All right, so here's what I would say. All right, both populations each individually follow a normal distribution. So I can say the population of medium cups follow a normal distribution. And the population of large cups follow a normal distribution. And because that's true, therefore, the population of the difference will also be normal. Okay. So if I was going to look at the population of the differences, okay, of all cups, that would also be normal. All right. Thus, if the population of difference is normal, all right, thus the sampling distribution of x bar L minus x bar M will be approximately normal. All right. Part B. It says find the mean of the sampling distribution. So I want the mean of the difference in sample means. Okay, that's what I'm looking for. Okay, just like before, all right, we said before if we had a single sample, mu of x bar simply equals mu. All right, well in this case, this would equal mu of L minus mu of M. All right, the population mean of large minus population mean of medium. All right, and we're given that data. So it's 27 minus 17, which is 10. So in my sampling distribution, the center of the difference would be at 10 ounces. Okay, if I took large minus the medium, should have a difference of 10 ounces. In part C, it says find the standard deviation of the sampling distribution. All right, so I'm trying to find sigma of x bar L minus x bar M. Now in this case, we do know the sigmas, okay, so we can use those. So that's going to be this big square root. So we would have, all right, sigma L squared over the sample size, all right, which is 20 for the large cups. Well, let me just write it like this, the sample size for the large cups first, all right, plus the standard deviation of the medium cup squared. Again, that means variance. Okay. If you think about why do you have to square these things? Well, same reason we had to square them here, because you can only add variances over the sample size of the medium cups. And when I plug in my numbers, okay, Sigma L was 0.8. Sample size was 20. All right, sigma M was 0.5. And the sample size there was 25. So we can do this in one step in our calculator. All right, big square root. 0.8 squared over 20 plus 0.5 squared over 25. 0.2049. That would be in ounces. All these are in ounces. Okay. Now, before I actually use that formula, okay, I should be checking the 10% condition. So is the population of large cups greater than 10 times the sample size of large cups? All right. So in this case, I think this is a pretty safe assumption. So we're going to assume the population has at least 200 large cups. And that the population of medium cups is at least 10 times the sample size of medium cups. Another pretty safe assumption, I would think. We're going to assume that the population has at least 250 large cups. All right, that's the independence condition. The only way we're allowed to use that formula is if it meets this independence condition 10 times the size. Right. So that's how we would calculate it. Now, just realize in real life we're not going to know sigma L. Okay. If we knew sigma L, we would know mu L. Right. Same way with the medium cups, and there would be no need to do inference. Right. That's just getting you used to doing the calculations. All right. So going on to the next part. It says the two sample Z and T test statistics, and these are going to be used in hypothesis testing. So read this next sentence. It is very unlikely that we would know the population standard deviations, sigma 1 and sigma 2. Okay, but if for some reason they are given to us, trust me, they're not going to be, then we would use the Z-curve and calculate a Z-test statistic. Otherwise, we would use the T-curve and calculate a T-test statistic. This is much more likely to be the case. Here are the associated formulas. As you can see, the only difference in the formulas is with Z, we are using a population standard deviation, sigma, and with T, we are using sample standard deviations. So it's very unlikely that we're going to use this. Because like we know, we're not going to know sigma. If we know sigma, we know mu. There's no point to do inference. This is what we're actually going to be using. We're going to be using a T-curve because this has to do with means. And when you have a means problem, you're going to be using T. So, when we do not know the population standard deviations, that would be sigmas, okay? And have to use the sample standard deviations instead. Those are S's, okay? Notice here in the bottom, instead of sigmas, you have S's. And that's why it makes it a T instead of a Z. Okay. We need to use the T-curve. This is the case in both confidence intervals and hypothesis tests. So, to use the T procedures, we have to check our conditions, same as before, random, independent, normal. If either population has unknown shape, because remember we have two of them now, and the corresponding sample size is less than 30, use a graph of the sample data to assess the normality of the population or the treatment distribution. Do not use two sample t procedures if the graph shows strong skewness or outliers. All right. Now here's the hard part of all this. Remember when we use the t-curve, there's a lot of different t-curves. There's a different t-curve for each degree of freedom. Okay. So when we had a single sample, the calculation for degrees of freedom was very straightforward. All right, so in a single sample, you just take your sample size minus 1. That's how you get degrees of freedom. All right. When we have two samples, the calculation for degrees of freedom is not so straightforward. We basically have three options to calculate the degrees of freedom. So option 1 is the most conservative. If you use option 1, this one would be the least likely to reject the null hypothesis. Okay, it's going to give you the smallest degrees of freedom. I'll give you the smallest degrees of freedom. You take the smaller of n1 or n2. All right, so in the previous example, I think NL was 20 and NM was 25. You would take the smaller of those, which is 20, and subtract 1. And in that case, you would get something like 19. All right. So that's going to give you the smallest degrees of freedom if you use option 1. And it's up to you which one you use, by the way. All right. Now, we're not going to show you, or we're not going to tell you to use option 1. All right. It says of all three options, this option provides the smallest degrees of freedom, just like we illustrated. This would result in the largest critical value and the widest confidence interval and the greatest p-value, which is not good when we are trying to reject HO of all three options. All right. Now, option 2, to find degrees of freedom, is called the Welch and Satterthwaite formula. For the purposes of this class, we will always use option 2. In the calculator, this is phrased as pooled no. Just remember when you use your calculator to do these, it's pooled no under the appropriate confidence intervals and test. And here's the nasty formula to calculate degrees of freedom. And we're not going to calculate this by hand. Okay? So what this assumes, okay, what this formula assumes is that your true population spreads are different, which is probably the case. Okay? If we have two unique populations, they probably have different standard deviations. So this option is the most appropriate most of the time. Okay. That's what this says down here. The degrees of freedom calculated by this formula assumes that the population standard deviations, these things, are truly different. It gives a confidence interval that is a little bit narrower than the first option, all right, and a true p-value. It's going to be weird when you see it, when the calculator calculates it. It's going to give you a decimal. Think about why, because you have a nasty formula that's a fraction. And if you actually do the division, it's going to result in a decimal 9 times out of 10. All right. So we're always, for our class, we're going to use this one. Okay. We're going to use that one, but we're not going to force you to calculate it by hand. All right. And option 3 is the most aggressive. All right, this does assume, this formula for degrees of freedom assumes that the population standard deviations are equal. Okay, and if you did that in your calculator, you would do pooled yes, but we're not going to do that. All right, just like it says, it assumes the population standard deviations are the same. All right, if you use this, it would give you the largest degrees of freedom, the smallest confidence interval, all right, the least wide, and the smallest p-value. So we're choosing the option in the middle. Okay, we're not choosing, the most conservative, and we're not choosing the most aggressive. So always use option 2, and remember, what you have to remember about that is pooled no, all right, and let your calculator assist you in determining the appropriate degrees of freedom. All right. So let's first talk about a confidence interval, how to do this part of inference for a difference, mu1 minus mu2. Okay. So with any type of confidence interval, we take our statistic or our difference of statistics plus or minus the critical value times the standard deviation of the statistic. And that whole thing that I just underlined in red, that's the MO, or the margin of error. All right. Now, not likely that we know sigma, so we're never really going to use that. Okay. We're not going to know sigma. If we know sigma, we also know mu, and if we know mu, there's no point in doing inference. All right, this is what we're actually going to use. Okay, this is the sample statistic. Now it looks like it's 2 statistics. It is, because it's a sample difference. Plus or minus the t star. Remember, your t star depends on your degrees of freedom and the level of confidence. Okay. Times the standard error. And this one has s's instead of sigmas, because we're likely to know s. We're not likely to know sigma. All right. Now, before we go through our full process of doing a confidence interval, we do have to do our conditional check, and we have to do those for both samples, or both groups. All right. We're going to follow that same process, SC, CDC, but with confidence intervals, we don't worry. There's no decision. All right. So let's go through this. All right. So in the first example here, it says the U.S. Department of Agriculture, which is the USDA, conducted a survey to estimate the average price of wheat in July and September of the same year. Independent random samples of wheat producers were selected for each of the 2 months. Here are summary statistics on the reported price of wheat from the selected producers in dollars per bushel. Okay. So July, I'm just going to call that my group 1. I'm going to write it in there to let the reader know I'm going to call that group 1. And this is group 2. September. It says construct and interpret a 99% CI for the difference in the true mean wheat price in July and September. Okay. So here we go. All right. First thing I do is I make a statement. And with a confidence interval, it's just telling the reader what I'm interested in estimating. We are interested in estimating the true mean difference, okay, which I would call, all right, mu1 minus mu2 of wheat prices per bushel in July and September. Is there really a difference? Well, the sample, it looks like there's a difference, okay? But maybe we just got 90 farmers that didn't produce great wheat, all right? Or maybe these 45 just were really good and had a really high quality of wheat. Okay, are they really different? All right. Is there enough difference here to suggest that there really is a difference. Maybe, maybe not. That's why we do a confidence interval. Okay. So that was the first part, statement. Part two, we have to do our condition check. Okay. Now, mu1, mu2, I probably don't have to say what those are because I called group 1 July and I called group 2 September. Okay. Or you can make it a little bit more clear, the true mean difference for all wheat producers. Okay. True mean difference for all wheat producers of wheat prices per bushel in July and September. So conditions, random. All right. Look at this sentence right here, independent random samples. Okay. So that applies to both. Okay, they were random for both. For both stated in problem. For both groups. All right, independent. All right, so we need N1 to be greater than 10 times sample N1. All right. So that's 10 times 90. So N1 should be greater than 900. All right, so we're going to make an assumption. Assume at least 900 wheat producers in July. All right, we have to do N2 greater than or equal to 10 times little n2, which is 10 times 45 or 450. All right. So we are going to assume at least 450 wheat producers in September. So we got two of the conditions done. I've got to go on to the next page, apologize. All right, now we have to do the third condition, which is the normal condition. All right. So here is sample N1 greater than 30. Yes, we had 90. Is N2 greater than 30? Yeah, what was it? I think it was 45. Yep, it was 45. It's greater than 30. So I would say something to the effect of both sample sizes greater than 30, therefore sampling distribution of X bar 1 and X bar 2 are both approximately normal by the CLT, thus sampling distribution of X bar 1 minus X bar 2 will also be approximately normal. So don't do this on your paper, but all right, since the first sample size is bigger than 30, that's the sampling distribution of X bar 1, approximately normal. Okay. then sampling distribution of x bar 2 will be approximately normal. So if I subtract these, then the sampling distribution of x bar 1 minus x bar 2 will be approximately normal. So it's important to say that. For each one individually approximately normal, so when you take a difference, that's also going to be approximately normal. Right. So let's go to number 4. All right, let's do a calculations. Or actually, sorry, this is step 3. Step 3 is calculations. Normal is still part of our conditions. All right, so this is a confidence interval. All right, it's a 2 sample. All right, this is coming from 2 different groups. T interval. It is a 2 sample T interval. And they're wanting a 99% confidence interval. And we're always going to choose pooled no. So I'm going to write the formula. All right. X bar 1 minus x bar 2 plus, that's my statistic, that's my sample difference, or the difference in the samples. All right. Plus my T star times my standard error, which is S1 squared over N1 plus S2 squared over N2. All right. All right. So we need to find all those values. All right. So x bar 1 was 295. X bar 2 was 361 per bushel. Okay. I'm going to leave the T star blank just for now. All right. Standard deviation of the first group was 22 cents per bushel over a sample size of 90. Okay. The second one had a standard deviation of 19 cents per bushel squared, because we've got to do that with variances, over 45. All right. So how am I going to find this T star? I need degrees of freedom. Okay. So as I look at T star, remember T curve is a little bit less. T star is a little bit less than a Z curve. It's fatter in the tails, doesn't go up quite as high. And I want 99% confidence. So I want 99% there. So there's only 1% left. So there's 0.005 in each tail. So if I look at the area to the left of where this T star is, all right, I'd have to do an inverse T with an area of 0.995. But I need to figure out the degrees of freedom. And this is where the calculator is going to come in. All right. So here's how we're going to do it or find it. I'm going to go to stat. I'm going to go over to tests. All right. I'm going to do a 2 sample T int. There it is right there, option 0, 2 sample T interval. All right, we're going to enter stats. X bar 1 is 295. Standard deviation is the 22 cents. All right, and the sample size is 90. X bar 2 is 361. Standard deviation is 19 cents. And the sample size there is 45. Okay. Confidence level 0.99. And we always have pooled no. All right, let's just calculate. When you actually hit calculate, it will tell you the degrees of freedom. 100.4483. 100.4482661. Right. Now let's use that. Let's not look at the calculator anymore. All right, and let's use that degrees of freedom in that area to actually figure out what the T star would be. So, I said not to use calculator, but actually we are. Sorry. So if I go to my distributions and I go inverse T, the area would be 0.995. Degrees of freedom would be that 100.4482661. All right, now I hit enter. All right, so my T star, my critical T, would be 2.626. I'm just going to store that as T. 2.62566. Right? So now, if I want to simplify that confidence interval, if I actually subtract these, the mean difference in the samples, what's that, about 66 cents, but negative? All right, plus or minus this T star, which we just said was 2.62566 times 0.22 squared over 90 plus 0.19 squared over 45. Let's figure out what that margin of error in total would be. So I'm going to take that number times the big square root. 0.22 squared over 90 plus 0.19 squared over 45. All right, so 0.096. And that's negative 0.66 plus or minus 0.096. Let me just store that as something. All right, so if I have negative 0.66 minus that number, or plus that number, all right, so my confidence interval is negative 0.564 if I round. Oops, it's on the high side. Negative 0.756 to negative 0.564. That's the actual interval. Let's check that calculation again by running that 2samp t int. Go down here and calculate. Negative 0.7561, negative 0.5639. Same thing. Okay, same thing. All right. Now, did you have to go through the manual calculation? Did you have to go through all of this on your paper? Probably not. Okay, probably not. All right. For this particular one, when we get into means where you have a weird degrees of freedoms and decimal degrees of freedom, okay, not really necessary to do all that. I would say to write that down, 2samp t interval, and tell the reader you're doing no pooling, okay, and then give the interval. Okay, give the interval. Okay, so let's ask ourselves, what does this actually mean? Let's do a conclusion. All right, I'm kind of running out of room for conclusion, so I'm just going to do this on another piece of paper. So conclusion. We are 99% confident. What does this actually represent? Okay. That the difference is, the true difference is somewhere between 75 cents and 56 cents but it's minus, so it's less. So July was less than September. Okay, that the true difference in wheat prices per bushel were between $0.756 really and $0.564 cheaper in July than September. So the true difference falls somewhere in here. They were less expensive in July than in September. So something to that effect would be your conclusion. Okay, put it back in the context of the problem. All right, so again, the hard part is figuring out this degrees of freedom. So we're going to let the calculator take care of that for us. Now, let me show you just the difference if you used option 3 here. Think about what option 3 would be. I would add these together, the sample sizes, which would be 135, and I would subtract 1 from each of those, so it would be 133 for degrees of freedom. So what would happen if I used degrees of freedom 133, okay, rather than this 100? Okay. So I want you to think about the t star here. Let's go to inverse t. Okay. So the same area, but what would happen if I did 133 instead of that weird decimal? Look what happens here to the t value. All right, the t value is 2.61, which would be slightly less than this. So this number would be slightly less, which would make the margin of error less, which would make this interval less wide. Okay, it will be a smaller margin of error, which means a less wide or a narrower confidence interval. That's the most aggressive one to use. That's the most aggressive one to use. Even though these sample standard deviations are fairly close, you know, it's probably the true standard deviations, the sigmas probably are not equal. Okay. So it would have made the numbers slightly different, and if you ran it on your calculator, okay, if you would have chosen pooled yes and calculate, okay, as you can see here, all right, slightly different. Numbers are slightly different. Degrees of freedom. Okay, it's 133 rather than weird decimal. Now, hypothesis tests are going to kind of work the same way. Right? Now, we can do one of two types of hypothesis tests. It all depends on whether we know what the sigma is, which isn't very likely, so we're not going to do that. Okay, we're probably not going to know sigma. Okay, so we can do a, this should be called a two-sample t-test, so just a slight error. Okay, for a difference between two means, two-sam t-test. All right. So generally, we're going to assume that the true difference is 0, okay, which means that they equal each other, right? And the alternative is that it's less than, one is bigger than the other, or smaller than the other. Okay, so our hypothesized value is usually 0. All right. Conditions exactly the same. as before. Okay. And it's recommended that we're going to follow the same process. All right, so let's look at this example. It says, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. Okay, so when it's an experiment, remember, you don't have to meet the independence condition. All right, it says the subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. So we don't have random selection, but we do have random assignment. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. And remember what double-blind means? The people getting the pills don't know which one they're getting, and neither do the people administering. All right, there's some master person that knows what everyone gets, but not the actual people themselves, not the doctors who give it to them or the people who take it. All right. It says the response variable is the amount of decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. So that's the units. An increase appears as a negative number. Here's the data. So for instance, this first person that got the calcium, he went down, okay? His blood pressure went down by 7 points. This person's went down 18, 17, 1, 10, 11. Now if it's negative, their blood pressure actually went up. All right, so part A, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? Okay, so carry out an appropriate test to support your answer. Now they did not give me an alpha, so I need to choose an alpha. Interpret the p-value you got in part A in the context of this experiment. So let's go through it. When we do a test, a hypothesis test for the difference of means, we're going to follow the same process. So step 1 is statement. All right. So my statement is going to involve a HO and an HA, a ho and a ha. All right. So I'm going to start by assuming that mu1 equals mu2. All right. Now, let's read what the alternative hypothesis should be, or think about what the alternative hypothesis should be. All right, do the data provide convincing evidence that a calcium supplement, so this group, reduces blood pressure more than a placebo? Well, more would mean there would be a bigger decrease. Okay, so the alternative hypothesis is actually that the decrease for group 1 is greater than the decrease for group 2. Think about why it's greater. Okay, mu1 is the true mean decrease for all healthy black men who take a calcium supplement. So I'm defining what mu1 is, and I'll define what mu2 is. That's the true mean decrease for all healthy black men who take a placebo or no drug. Remember, in experiments, especially medical experiments, we give a placebo to see if there's a psychological effect. All right, a placebo effect meaning that someone thinks they're getting medication and they feel better just by thinking that they're getting medication. All right, so there's our statement. All right, in step 2, we have to do our conditions. All right, so random does not mean random selection in an experiment, because you can't randomly put people into an experiment without their consent. It's about random assignment. Okay? So I can say that random assignment is stated. All right. Independence is the next condition. In an experiment, large counts condition does not need to be satisfied. Okay, that's that capital N greater than 10N. Okay. And the normal condition, still have to worry about that one. All right, so going back over everything in here, we have no information about the population. All right. Now, there's 10 men who get the calcium. There's 11 men that get the placebo. No way that these are both 30. The sample sizes for each group is not 30. Okay? So, we can't apply the CLT. All right? So, what I would say here is population shape unknown. All right, and I would say N1, N2 are both less than 30. So the CLT does not apply. But remember, we're going to be using T procedures. We are going to be using T procedures, all right, which are robust. All right, so what I have to do here is I have to take this data and put it into a list to make sure that there's no outliers. All right, so I'm going to put group 1 into list 1, 7, -4, 18, 17, -3, -5, 1, 10, 11, -2. All right, I'm going to put data from the second placebo group into list 2. And it might look kind of funny, but remember, group 2 has one more data point than list 1 does. All right. Then I can plot these. I can go under my stat plot, turn it on, and do modify box plot of L1. Okay. So I'm going to do that. And then I'm just going to zoom 9 in. Okay. So I can draw that box plot if I want. Kind of looks like this. And I can say group 1 shows no outliers. Okay. Now if you want to put the values, you can. All right. Min difference is -5. Q1 is -3. The median is 4. Q3 is 11. And the max is 18. And that's my 5-number summary. All right, now you can do the same thing for the second group. So I can just go back, and instead of doing L1, I can just L2, and then I can zoom 9. That one looks more symmetric, the placebo one. All right, so I can copy that one, much longer tails. -11, -3, I'm just tracing on my calculator, -1, 3, 12. Group 2 shows no outliers and relative symmetry. All right, so I would say something to the effect here that T procedures are robust. So we will assume the sampling distribution of x bar 1 minus x bar 2 is approximately normal. Now, step 3 is going to be my calculations. And this is a 2-samp t-test. Now, they did not give me an alpha. You choose, when they don't give you an alpha, you have to choose the alpha. All right, so alpha, it's medical, so I'm going to be a little bit more stringent than I usually would. I'm going to pick 0.01 as my alpha. And remember what these hypotheses are. Another way to write that hypothesis is that if I take the difference, it would be 0. Right? And this, if I just subtract u2 from both sides, the difference would be greater than 0. You can rewrite it those ways. All right, so my test statistic here is going to be t equals the x bar 1 minus x bar 2, that's the statistic, minus the hypothesized parameter is 0, over big square root s1 squared over n1 plus s2 squared over n2. That would be my test statistic. Okay. Now watch how I can do this on the calculator. Stat, go over to test, 2-samp t-test, option 4. All right. We actually have data. Okay. List 1 is an L1. List 2 is an L2. They both have frequency of 1. Your alternative hypothesis is that mu1 is greater than mu2. And remember, we choose pooled no. All right, and let's calculate. So it gave me all of these things. Now, if you're not going to do it by hand, at least give the reader what the statistics are. So you can scroll up and down here to find all these. So x bar 1 is it's 5. X bar 2, okay, so I'm just copying it from my calculator, it's negative 0.27 repeating. All right, S1 is 8.743. S2 is 5.901 if I round. N1 is 10. N2 is 11. All right. And let the reader know what degrees of freedom you're using. So degrees of freedom equals 15.5905 roughly. If I would have taken the most aggressive, if I did option 3 for degrees of freedom, I would have got, well, 10 plus 11 is 21, minus 2 would be 19. Okay. We would have got 19 if I would have chosen pooled yes. Right. So when you do that, let's just stay in the calculator here. It gives you the test statistic. That's right there. That's the 1.603. That's the test statistic. So if you were graphing this t-curve, 0 would be down the center. Your t-value would be 1.603. And based on the alternative hypothesis, you would be shading to the right. So that would give you a p-value of, right here, 0.0644. That's the p-value. .0644. So that's the whole purpose of the calculations is in a hypothesis test, to get your test statistic and to get your p-value. All right. Now, not quite done yet. We still have to do our decision and our conclusion. Okay, so 4 is the decision portion. Well, in our case, the p-value was about 0.06, but I chose an alpha of 0.01. So the p-value is actually greater than the alpha, so the p is not low here. When p is low, you reject the O, this one's not, so we fail to reject the null hypothesis. All right, so what does that mean about my conclusion? There is insufficient statistical evidence at the alpha equals 0.01 level to conclude that calcium supplements decrease systolic blood pressure in healthy black men. Okay, because the mean decrease was not actually greater. There wasn't enough evidence. Okay, so we just say that they're the same. The mean decrease is going to be the same, or we can't get rid of that assertion. All right, so that's that problem. All right, I'm going to stop this video here, and I'll finish it up in another video. This one's just gone a little bit long, so yeah, we'll just work this one on another video.